In March 2011, the magnitude 9.0 Tohoku earthquake triggered an extremely destructive tsunami that killed thousands of people, caused widespread liquefaction, and resulted in tens of billions of dollars in damage. A single dam failed during this event, which is Fujinuma Dam. This presentation is about the geomechanical numerical modeling that was performed to understand how Fujinuma Dam failed. The scope of the presentation will include an introduction, a description of the failure of the Fujinuma Main Dam, the numerical modeling of the failure of the main dam, and a small description of the rapid drawdown failure of the auxiliary or saddle dam. The Fujinuma Lake is retained by two dams. The main dam is about 60 feet in height, and the saddle dam is about 20 feet in height. The lake is relatively small and is about 1,200 acre-feet in volume. This is a picture and a cross-section of the main dam that was prepared well before the failure, and the cross-section also shows some of the piezometers that were installed a long time ago on the dam itself. At the time of the earthquake, the reservoir was full, and 20 to 25 minutes after the earthquake, the water was seen overflowing the crest of the dam. The water flowed through a narrow canyon and destroyed a village located at the mouth of the canyon, killing 9 people. This is a picture taken about 25 minutes after the earthquake that shows the dam being destroyed by overtopping. When I visited the site in April of last year as part of an ASCE reconnaissance team, the dam was completely destroyed and also had a bridge near the right abutment that had been carved by the flow of water. One of the key observations made during the site inspection was that the dam was made mainly of cohesive materials that stood up to relatively high heights without any need for support. The numerical modeling of the failure of Fujinuma Main Dam was performed using version 7.0 of FLAC, a program created by Itasca. This slide shows the mesh that was used, and you will notice the different zones where different strengths were placed to model the materials of the dam and of the foundation materials. In order to model the seismic behavior of Fujinuma Dam, we also looked at the ground motions that were recorded around the Fujinuma Dam itself. The circles and the squares show where seismic stations were located, and for one of them you will notice that the maximum ground acceleration was approximately 0.4 Gs. This is the ground motion input that was used in the numerical modeling. It was from a station located near the dam on bedrock. You will notice that most of the shaking occurs between a time of 40 seconds to about 160 seconds. This is a video in which the deformations of the dam have been exaggerated 5 times. You will notice that at the beginning you're seeing a lowering of the crest elevation, also a small displacement of the toe. The colors that you're seeing right now show a concentration of shear strains, and when this sliding takes place, there is an even more lowering of the crest elevation, resulting in approximately 2 meters of predicted displacement by the time we reach 160 seconds. This mode of deformation would allow for water to overtop the dam, leading to the failure that was observed by overtopping about 25 minutes after the beginning of the earthquake. The saddle dam failed towards the upstream side of the dam, or towards the reservoir, as you can see in this picture, and resulted in a near total failure. Just like for the main dam, we did not see any evidence of liquefaction on the downstream side of the saddle dam or on the abutments, and the same was true for the main dam. This is the mesh we use for numerical modeling of the saddle dam, and when the reservoir was lowered, the phenomena that takes place is that for failure surfaces such as the one in the dashed line, there is no time for the water pressures to exit the dam, so that water pressure is still locked in within the saddle dam and pushes or creates uplift on the dashed yellow line that you have here. This type of failure is typically known as rapid drawdown, and when we analyze numerically the likelihood of these type of failure, we came up with a factor of safety of less than 1, which means failure. The color contours show the concentration of shear strains. The arrows show the direction of movement for the critical mode of failure that has this very low factor of safety. These rapid drawdown mode of failure is the likely mode of failure for the saddle dam that you see in this picture here. On behalf of everyone at Group Delta, I hope you enjoyed this presentation, and I wish to thank you very much.